In this video, I'm going to show you how to model non-equilibrium condensation of superheated steam under supersonic flow conditions. So I will just open my custom tree and show you the geometry first. So let's open our mesh scene. Yeah, we have here our mesh scene. So we have the inlet and outlet. At inlet, we have steam at 1.5 bars, absolute at 130 degrees Celsius. At outlet is environmental flow conditions. So we have our initial temperature here, it is parameterized, and our mesh is directed mesh, polyhedral cells, and we have prism layers on the walls. For running this multi-phase case, first we would like to run it in steady state to calculate the supersonic flow field before moving to the multi-phase. So therefore we have two continuous here, one single phase, one DMP. Let's switch to the single phase and run this case. So we have the single phase and start the run and open our layout view. So you can see here various plots and scenes. We have residuals, we have some mass imbalance, and we have also monitor points that we already defined. So as seen, we have the Mach number, temperature, and absolute pressure. You can see supersonic flow is already developing. So we have here different monitor-based stopping criteria for the single phase flow. We are using here volume average temperature and volume average velocity, and they are going to converge with a tolerance of 1% in 200 iterations. So the single phase simulation is done. Let's switch to the multi-phase simulation using DMP. For the DMP simulation, especially for the condensation, we have an important parameter here is the saturation pressure. So we would like to see how we define it under continua. So we go to the gas material properties here, and then under saturation temperature, we can define saturation temperature, and under saturation pressure, we can define saturation pressure based on the temperature. Here I've used a field function, a polynomial field function. Let's see this field function in detail. Just switch to the field functions. So the saturation pressure you can see here defined polynomially. Then just give a temperature range. Say we have something like 270 Kelvin till 600 Kelvin. So as you can see here, the definition of the saturation pressure based on the temperature that we have is nonlinear. And if you look at the background for the results of the single phase simulation, our temperature range is between 285 till 403. So we are in this nonlinear region. Yeah, let's close this and run the simulation. Is done. The multi-phase simulation is converged using two more monitor-based convergency criteria. As you can see here is the volume fraction of water at the outlet and volume average volume fraction of water. Both of them were converged using 200 iterations with a deviation of 1%. So if you look at the flow domain, you can see also the volume fraction of water. At the beginning, we don't have any water in the system. So after just having very high temperature and pressure gradients, the condensation occurs. And our mass imbalance is also quite good.